As I gathered the material for this video, which explains how I motorised my 9F Loco, I began to realise that there was too much content for one video, so this is part 3A. My Hornby 9F has no motor in the locomotive. All the tractive effort comes from the tender. Because of the difficulties of fitting motors into the Winston 9F, I did consider that approach, but decided that I should make the effort. Once the loco was on my bench, which was no mean effort since it weighed about 170 pounds, I set about separating the superstructure from the chassis. The bolts came out easily, and soon I was ready to lift the boiler, cab, cladding, etc. all in one piece. Having tied the running boards to the boiler with some cardboard as protection, I threaded a steel pipe in through the smoke box and out through the coal hole. Then two of us lifted the assembly and put it safely on some cushions upside down. I removed the ash pan and was then able to see inside the firebox. There were various projections which I later ground off with a tungsten carbide tool in a Dremel. There didn't seem enough space to fit in 250 watt Fasco motors, but after a few calculations it looked like I might be able to squeeze in a single 250 watt Fasco. There was plenty of room in the tubular part of the boiler, but that would make disassembly too difficult. The main problem was that I didn't have any Winston drawings of the boiler. However, there was a rumour that Winston had simplified and metricated the Warnit drawings, so I bought a set of these and scaled the appropriate area as near as I could to my boiler. Using lots of cardboard cutouts, I began to formulate a plan. It would have been easier to drive the fifth axle, but this would have meant that the necessary play in the system would accumulate towards the front. Powering the centre axle was the approach of the steam prototype, and I decided to adopt that idea. I considered a tooth belt, but that meant that any change in the dimensions would require a new belt. Anyway, I thought that a metal chain was more in keeping. I had a copy of the HPC gear catalogue. This was a marvellous publication that not only gave the dimensions OD, ID, BCD, thickness, etc. of the huge number of gears and sprockets that they can supply, but also lots of design guidance. This diagram shows the principle of the idea that I settled on, but I have truncated the distance between the centre axle and the gearbox so that I can get all of the image onto a single A4 page at a reasonable scale. I refer to this unit as the gearbox, though most of what it contains is sprockets. Somehow, sprocket box sounds rather odd. The sprockets and chain are shown in green. Using the HPC data, I settled on 3/8, that's 9.5mm chain, and an 18-tooth centre axle sprocket. 18 teeth was the minimum size recommended for drives, although smaller sizes can be used for idlers. Anyway, this 18-tooth sprocket S2 was a very suitable size for the centre axle, ensuring adequate clearance between the chain and the sleepers, and had a big enough hub size to accommodate the axle. It's probably easier to describe the system with the locomotive being driven in reverse. This requires S2 to be driven clockwise by tension in the chain between S2 and the 18-tooth sprocket S1. S3 is merely a 13-tooth idler. S1 is fixed to the same axle as the 140-tooth nylon gear G2, which in turn is driven by the 17-tooth motor pinion G1. On the return path, the chain passes around a 13-tooth idler S4. Some slack is required to accommodate the up and down movement of the suspension. S4 is mounted on a swinging arm provided with an adjuster to set the slack value. Even though slack is required, droop of the chain between S4 and S2 might allow the chain to touch the sleepers. To avoid this, a Delrin rotating follower, F2, shown in yellow and mounted on a swinging arm, is held against the chain by a pair of springs. When the train is being driven forward, the chain round S4 is in tension, and the follower F1 now takes up the slack. The two tension springs are fitted between the pivots of F1 and F2. I've only had one day of learning to use LibreCAD and zero experience of any other non-electronic CAD package, so drawing springs was beyond me, but you should be able to pick them out later on the photo. The sprockets S1 and S2 were chosen to be the same, so that the axle of S1 would rotate at the same speed as the axle of S2. I plan to incorporate a 4-section flag on S2 axle with an infrared slot sensor to control the chuffs synchronized with the piston position. The 17 to 140 gear ratio, together with the larger wheels, worked out serendipitously to give virtually identical motor RPM to that of the tender at the same track speed. Before building the gearbox, I needed to ascertain the state of the running gear. With this in mind, I made a simple piece of track on a wooden board and devised a jack system to raise and then lower the heavy chassis, so that the board could be slipped in from one end without effort. Moving the loco backwards and forwards a short distance showed that there was much work to be done. To get a better idea, I built two rotatable end units, which used together could hold the loco at any desired angle. Whoever had put the loco running gear together had made a pig's ear of it. I decided to get some help and took the chassis over to Link's Model Works, while I got on with the detailed design and construction of the gearbox. They kept the chassis for a long time and charged me a lot of money. They may have made excellent model steam locos, but as far as sorting out the Winston chassis I was not impressed. In the end I had to do much of the work myself. I removed the links, rods, etc., and all the wheels and axles. I cleaned up the wheel mating surfaces, sorted out the fit of the axle blocks, and re-Loctited the wheels in my lathe. Dealing with the suspension was the next task. The Winston springs on this model were badly constructed and didn't work. I started remaking them, but then had a rethink. What it really needed was a system that was reliable, worked well, and was simple to adjust. Since the suspension was underneath and could not be seen, my electric loco really didn't need to use leaf springs. Rubber suspension had worked well on the tender, so I came up with the design shown in the photo. The axle blocks were already tapped 2BA, so I made new threaded rods and locked them in place. Flat rigid plates with central clearance holes were then bolted on in place of the springs. I bought some conical black rubber stoppers and bored clearance holes through them. I then put each one onto its threaded rod, followed by a washer and an adjustment nut. When tested, this worked very well. The pony truck had been put together badly, and some parts were missing. It required a major rebuild, and parts of the loco side frames had to be reshaped to allow a suitable arc of side-to-side travel. When all this was assembled, I tried pushing the loco on my first length of track. It would run, but not happily. Various parts of the rods and linkages needed attention. This is a convenient point to stop the video. So far I've only dealt with the principle of the drive system. In part 3b I will delve into the construction of the gearbox and its associated parts. I'll also cover the modifications of the superstructure, show the chassis running, and include some early sketches and calculations.